let's see. Okay, I'm going to give you a quick rundown of linear transformation 1.8 and 1.9. So definition of linear transformation, or we can say linear mapping. Okay, T okay, is defined by if mapping is defined by like this, then we can say the T is linear transformation, or we can say linear mapping. So linear transformation T satisfies two conditions. There's one, T of U plus V. U and V are column vectors. Is equal to T of U plus T of V for all vector U and V in domain of T. Okay, so in the domain. Second condition is that T of C times vector U, C is scalar, is equal to C times T of U. And for all U is in the domain, okay? And then C is in the real number. All right. So matrix is, last time I told you, matrix represent the linear transformations. So T of X is defined by AX. So since linear transformations can be represented as a matrix multiplication. And then since A has a size, right? Number of row, number of column, saying A is n by n matrix, then T is mapping from Rn space to Rm space, right? So here's a fact about the linear transformation. If T is a linear transformation, then T of zero vector is equal to zero vector. And then the first one. The second one, the linear transformation of U plus dV is equal to, we can just now decompose the linear transformation of the linear combination of vector as linear combination of mappings. So T of vector U and plus T times T of vector V. Okay. So here's a proof. Why T over zero vector is zero vector? Zero vector because T of zero is equal to we can say T of zero vector plus zero vector. Okay. It makes sense, right? So now then what are you going to do? Keep in mind this, we do not know this one is equal to zero vector. That's what we want to claim, right? What we claim is that T of zero vector is a zero vector. So we need to derive zero vector from this. So I'm going to use some trick. That trick actually. So this is by the linear combination. I mean the property, the first one of the linear combination. We can decompose this one as T of zero vector plus T of zero vector. So you see, this one is equal to this one. So T of zero vector is, well, 2 times zero vector is equal to T of zero vector. So I don't know what that the value of the T of zero vector, but we can say you can say that subtracting T of zero vector on both sides, then T of zero vector is going to be zero vector. Proof is done. Okay, so the proof of the first one. The proof of second one. Okay, let's say I mean a second. I think this is obvious. We don't have to prove it, but okay. So T of yeah, this is let me skip proving this because using the linear transformation, the two conditions of the linear transformation, we can easily can prove, you know, this one is equal to this. So let me skip it. Next one, let's see. Let's say theorem. Theorem. I think theorem 11. Let me prove theorem 11 first, and then we'll back to theorem 10. Okay. So if the T is a linear transformation from N to Rn space, okay, which means that the matrix A in the linear transformation is N by N, okay? So this is linear, and then T is 1 to 1. Yeah, 1 to 1. If and only if T of X is equal to 0 vector, has only the trivial solution. Okay. Here's proof. What does that mean? So if T is a linear and 1 to 1, so 1 to 1 means that what? For each X value, I mean input, there exists only one corresponding Y value, right? Okay. And then distinct also. So T of X equals 0 has the only trivial solution, means that the input of the linear transformation returning 0 vector has only one, right? Okay, why? Okay, so here's let me prove that way first. So this is trivial because if a T is a linear, then the seed effect T of 0 vector is 0 vector, right? So that's trivial. Okay. So because a T of 0 vector is 0 vector. So I just proved that, right? Okay, and then we prove that way. Suppose that we assume that T of X is 0 vector has the only trivial solution. Okay. Suppose that T assume this, okay, we assume that, and then suppose that T is not 1 to 1. I think this is a key. That's the main assumption when we establish this theorems. Okay. So T is not 1 to 1. If T is not 1 to 1, then there exists. Okay, that's a symbol of existence, okay? There exists. There exists vector B, which is in our M space, right? What does that mean? T is not 1 to 1, which means that, let's say this is a domain, this is a codomain right here. Then this is Rm, so Rn. This is Rm space. Okay, so that's a linear transformation. T of X is equal to Ax. Right here. Then here's a point right here, input. I don't know, maybe X. Okay, since T is not 1 to 1, we suppose that. So this one goes to right here. Let me say U, vector U goes to vector B. Then there is another vector V, saying V goes to vector B. Okay, so this is a mapping, or we can say function, but we cannot say that this is 1 to 1. Yeah, so suppose T is not 1 to 1, then there you could use the vector B in Rm space such that what? T of U is equal to vector B and what? T of vector V is equal to B. Okay, so here two vectors are in Rn space. Okay. And then yeah, and definitely two vectors are distinct. Okay. Then what? T of vector U minus T of vector V is equal to, because T is a linear transformation, so satisfy linearity, which means that we can combine, right, two transformations, vector U minus vector V, which is equal to, so what is this? T of U, we assume that this is equal B, right? This is equal B, right? So this is equal to B minus B, which is 0, right? B minus B, which is equal to 0 vector. So here, because T is linear. So T of U minus V is equal to 0 vector, and U minus V is equal to 0 vector. This is not equal to 0 vector. Okay. So what does that mean? So thus, T of X is 0 vector, has non-trivial solution. Okay, that's non-trivial solution. That's problem, right? What? We assume that T of X equals 0 has the only trivial solution. That's the assumption. But we got non-trivial solution. Okay, where from, from where we went to wrong? Right there. Because of that assumption, supposition, because we suppose that T is not linear, that's why this one lead to the wrong, contradiction. Okay, this is a contradiction, right? That's a symbol of contradiction, okay? That's a symbol of contradiction. So therefore, well, T must be linear. So I mean T is linear. Okay. So yeah, that's proof is done. Okay. So here, proof is done. Yeah. So keep in mind this. If T is a 1-to-1, then T of X equals 0 vector has only the trivial solution. Yeah. So what does that mean? T of X bar equals 0 vector has only trivial solution, which means that what? That X bar must be 0 vector because of that fact. Right? So if T is a linear transformation, T of 0 vector equals 0 vector. And then theorem 11 says that if T is linear and then 1-to-1, then this guy has the only trivial solution, then X bar must be 0 vector. Okay. So expressing this one in terms of matrix form, T of X bar equals 0 vector, it means that what? A X bar equal to 0 vector. This is homogeneous, right? So T is 1-to-1. The matrix homogeneous system has only trivial solution, and then that solution must be 0 vector. That's what this theorem says. Okay, so right here, and then this is a question right here. What if we have a linear transformation? E from mapping from Rn space to Rm space. Okay, and know how it acts. Okay. On some factors. But don't have the formula for it, which means that we don't know matrix A. Since, okay, we know how that acts. We need, It means that, okay, so let's say we know the behavior of this linear transformation. I mean, maybe we know the graph or some information of the linear transformation, but we do not know matrix A. How can you figure out matrix A? That's the question. Okay. Don't have a formula. Wait. So how can you get it? So here's the answer. So how? Okay. Good. So here's the answer. Examples. Let's get some clue from the example. Okay. Think about the linear transformation R3 to R2. Okay. So and then E1 says standard basis vector. Standard basis vector is a column vector on each axis in a dimension. Okay. And has a length 1. It's kind of the unit vector in vector calculus. So E1 and E2 is 0, 1, 0. E3, 0, 0, 1. Okay. So E1, E2, E3 is kind of this one here, here, here. So axis, x1 axis, x2 axis, and x3 axis. So this is E1, this is E2, this is E3. Standard basis vector, or standard unit vector. Sometimes it's called E1, E2, E3. So let's see. Now, see, can you see? For example, T of E1 vector return 2, 4. Okay. The T of E2 return 0, negative 1. Okay. And T of E3 is return 1, negative 1. Okay. And let's find the matrix A such that A of X is T of X. Okay. Find the matrix A such that A of X bar is equal to, I mean, T of X bar, you know, or is equal to 8. Okay, so now this is equal to, yeah, so then what you're gonna do, we're gonna think about this. We just observe 3 given informations. T of E1 is equal to, okay, T of E1 is equal to A times E1, right? Because we don't know E1, A. Okay, so this is equal to what? 1, E1 is what? A times E1 is 1, 0, 0, right? This is equal to 1 times what? What's this? 1 times what? Yeah, first column, right? A1. A plus 0 times A2 plus 0 times A3. So here A1, A2, A3 means that columns of matrix A. If you just say A is A1, A2, and A3. So A1, A2, A3 columns. Okay, how can you guarantee that matrix A has 3 columns? Because here we say T is mapping from R3, R2. Then the matrix A gonna be size gonna be 2 by 3 matrix. Keep in mind this. Now T of X bar is mapping from Rn to Rm space. M space, then what? The matrix A in this linear transformation, size gonna be n by n. Okay, keep in mind this. So, since T is R3 to R2, so A is 3 columns. So, yeah. So we can say, okay, A1, A2, A3 are column vectors of matrix A. Okay. So then this is going to be 1 times A1 plus 0 times A2 plus 0 times A3. So now you see 0 times A2 is gone because it's 0 vector, and the 0 times A3 is 0 vector. So 0 vector is 0. This is equal to A1. A1. Okay. So, but we know T of E1, what it is, 2, 4, right? Isn't it? This is equal to 2, 4. Okay, likewise, then we can figure out the second column and third column of matrix A using the rest of, the information given in problems. T of 2 is this, T of 3 is that. So similarly, T of, T of E2 is equal to A times E2, right? So this is equal to A2, right? That must be equal to what? 0, -1. Okay, and T of E3 is equal to A times E3, right? This is equal to A3, that is equal to 1 and -1. Okay. Um, so now, yeah, so we figured out, finally, we got matrix A. So T of X bar is equal to A is what? 2, 4, 0, -1, 1, -5. Okay, times X bar, which is X1, X2, we can say that. So this is a matrix A. That is matrix X. Input, column vector X. So you got the information of matrix T. I mean, when T of T of E1 through the T of E, yeah, M, right? N, sorry. Okay. Then you can find out matrix A. Okay. So actually, what here we can see that T of E1, T of E2, T of E3, these are what? Columns of matrix A. Okay. So if you want to figure out the columns of matrix A, then what? Just plug in standard basis vector into the linear transformation. Then that will return the columns of matrix A. Okay. So from here, okay, so let me write the theorem 10. Theorem 10. So if a T is a linear transformation from mapping from Rn to Rm, okay, it's a linear transformation. Okay. Then there is a unique matrix A. Okay, this is theorem talking about uniqueness of the matrix corresponding to the linear transformation. Linear transformation, then, okay, there exists a unique matrix m by n, or m by n matrix A such that T of X is equal to AX. Oops, this is AX. Okay. For all X is in what? Rn space. Okay. So and then yeah, and the matrix A is actually what? T of E1, T of E2, right? Through the T of En. T of En. So that's now you see the relationship between the matrix and the linear transformation, right? Okay. So E1 through En is what? Standard basis vector. Or you can say these are E1 through En are column vectors of the identity matrix. You know, think about In. In is what? 1, 0 through the 0. The 0, 1, 0 through the 0, right? Here's a 1. It's okay. Here's a 1. Okay, here's a 0, 0. Simply, this is a diagonal matrix with diagonal entries are 1. Okay, so this is m by n. So each columns are standard basis vectors. This is E1, E2, E3, okay, through the En. So now let's see example. Okay. So let's say linear transformation from R2 to R2. It's kind of nice because it's the dimension of input and output. I mean, dimension of domain and codomains are identical. Right? So let's say the linear transformation T rotate the points counterclockwise about the origin by angle theta. So what kind of the linear transformation T do that? So I mean, how can we construct the matrix A so that the linear transformation uh operate like that? You know, the rotating, let points rotate counterclockwise about the angle of theta. We're gonna use this T of E1. Think about this right here. Then to figure out that we need to construct T of E1 and T of E2, right? This is R2 to R2. Okay, sorry. This is 2, not N. It's typo. So this is here X1 axis, and this one is X2 axis. Okay. So X1, I mean E1 is, where is E1? E1 is right there, right? E1 is right here. This is E1, which is 1, 0, right? Okay. And then rotating. Rotate means that what? The point, the end point of this vector must be a move along the unit circle, right? So let me draw a unit circle. Okay. So moving this one to maybe, you know, let's say we want to rotate the E1, this point counterclockwise by angle theta. Theta is right here. This is theta. Nice theta right here. Okay. Right. Okay. Point. What's the coordinate of this point? The coordinate of this point is going to be cosine theta and sine theta, isn't it? Okay. That means the vector of this, that's a vector whose the terminal point is this point going to be this cosine theta and sine theta. Okay. So we want to get this one cosine theta, sine theta when you put when you just put the E1 into the linear transformation. Sine theta. Okay, let's figure out the linear transformation of E2. Because this is R2 to R2. So we need to think about two standard basis vector, right? E1 and E2. E2 is, where is E2? E2 is right there on the X2 axis, vertical axis, right? So let's say this is E2. Here's E2 right here. So the rotate, we're gonna rotating E2 along the unit circle with the angle theta counterclockwise. And we're gonna get right here. See right here. It's gonna be This is data, right? That's the data. Okay. Then what's the coordinate of this point? Anyone can figure out the coordinate of this point? What is it? The coordinate of this point going to be minus sine theta, cosine theta. Yep. So we want to get this one when you put E2 into linear transformations. So let me just copy it. Now cosine theta. Okay. So linear transformation T of x bar is defined by AX. Okay. So now here A going to be what? This means that that is here. That means that what? This is going to be first column vector of the matrix A, and this is second column vector matrix A. Okay, just combining everything, so that we can finally we could figure out the matrix A, cosine theta, then minus sine theta, then sine theta, and then cosine theta. So here now then, okay, geometrically this linear transformation rotate the points counterclockwise about the origin by angle theta. Right? So there are more the linear transformations that can transform geometrically. That is in the textbook. Okay, so I think 6 special, interesting linear transformation introduced in textbook. So please look at it. So here, and then let me introduce theorem. Let's see, theorem 12. Theorem 12. So let's say E linear transformation mapping from Rn to Rm space. Okay, be a linear transformation, and A be a matrix of T. Okay, be a linear transformation. And A be the matrix of T. And let A be the matrix of linear transformation T. Then first one, A. So T map from Rn to Rm, Rn onto Rm. Okay, if and only if the columns of matrix A span Rm space. So A span Rm space. Okay. So what does that mean? Columns of A span Rm space, which means that the columns of matrix A generate the linear combination. I mean, the set of all linear combination of the columns of matrix A is equal to Rm space. So then to do that, every columns of matrix A must be pivot columns. Okay, second one, T is 1-to-1. This is 1-to-1. Okay. If and only if the columns A are linearly independent. A are linearly independent. Okay. Okay, let's prove it. Okay, prove. First one, A. Okay. So we're gonna use the theorem 4. Okay. So by theorem 4. what? The columns of matrix A span Rm space if and only if Ax is equal to B1 is consistent. So for all B in what? Rm space. This is consistent, which means that the matrix equation has at least one solution for each B. Okay. So if and only if. Okay. Think about this. The columns of matrix A span Rm, then by theorem 4, that matrix equation is consistent for every single matrix B, column vector B. Then this consistent, which means that what Ax, the matrix equation has at least one solution. That's the definition of consistent, right? For all B in Rm space. Okay. So now what? Which means that T map from Rn onto Rm space. T map Rn onto Rm. Okay. Rn onto Rm. And then B. Since T is a one-to-one, then if only if the columns of A are linearly independent. All right, so we're going to use the fact we saw in theorem 10. Okay, since T of x bar is equal to 0 has only one solution, unique solution, right? So if and only if Ax bar is equal to 0 vector, which is homogeneous system, right? This is if and only if this. Okay, because of theorem 10. Right. So because of that, Ax bar is equal to 0 vector, which has the which is a homogeneous system, right? Homogeneous system has only trivial solution. If and only if what T of x is equal to 0 vector has only trivial solution. Then what? This one has only trivial solution. Then by theorem 11, T must be 1-to-1. That's why I proved theorem 10 and 11. We saw theorem 11 and 10 first. To prove a theorem, the second statement of the theorem 12, we saw theorem 10 and 11 actually. 11, right here. Purpose. Right? I mean, okay, not done yet, but almost done. In the sense, the Ax, the homogeneous system, has only trivial solution. Oop. Yeah. So, solution if and only if the columns of matrix A are linearly independent. Yeah. Because of this statement, T is 1-to-1 if and only if the columns of A are linearly independent. Okay. Okay, so let's see, linearly independent. This has only trivial solution. The columns A are linearly independent. That means what? T is 1-to-1, if and only if the columns of A are linearly independent. Okay, perfect stuff. Yep. So, okay. So here's a proof right here. Yeah. So keep in mind is there are a lot of there are many but the statement equivalent to the onto and one-to-one. So please look at textbook. Okay. So that's for theorem 1.8 and 9. Okay. So I did go over major theorems in 1.8 and 1.9.